All right, we've got 6 problems to work on. This is the Calculus 1 Exam 2, Spring 2024. Let's do it. Number 1. Use logarithmic differentiation to find dy dx if y equals x times cosine x to the power x. Now there's 2 schools of thought when it comes to logarithmic differentiation. One school of thought is the implicit route. And it says the following. Say, hey, take the log of both sides. And so we'll say this is the implicit route, namely log of y equals log of x cosine of x to the power x, and then move forward. I am not in that camp. The second camp, this is the formula route. And here's the formula. It says, look, if I want to take a derivative of f of x, I'll call it f prime of x. It is f of x times the derivative of the natural log of f of x. And so I'm just going to plug it in, right? Because we're asked to find the derivative. Let's do it. Okay, so we'll grab a pen here. And we say, what do we have? We have our dy dx is equal to, okay, according to the rule, write down the function again. So whenever you're doing logarithmic differentiation, your function shows up at the end. Oh yeah. So we have x cosine x to the power x times the derivative of the log of x cosine of x to the power x. Lots of parentheses there, but parentheses are friends, so we don't mind. You'll see that we still got to the same place when we took the formula. Now, why are we doing logarithmic differentiation? Because of logs. They have these cool things. It lets us pull stuff apart. So multiplication becomes addition, division, subtraction. Exponents, they come on down. Come on down. You're the next contestant on logarithmic differentiation. So, what do we have? We have the function again. And this is one unfortunate side effect of logarithmic differentiation. You write a lot. All right, now we're not taking the derivative because the whole point of logarithmic differentiation is first, simplify it. We're pulling it apart into pieces. And by pulling it apart into pieces, we turn a big problem into lots of little bitty problems. And then life is good. So multiplication, see there, that we're going to separate log x. And then here we have log of that term. But there's an exponent. Exponent comes on down. X log cosine x. Great. Now we're ready to take a derivative. So, again, we have x cosine x to the power x in the front. Okay, the derivative of log x. Well, the way I always think about the derivative of logs, it's 1 over the inside, and then times the derivative of the inside on the top. So derivative of log x, 1 over x. Here, product rule. So derivative of the first is 1. So you have 1 times log cosine of x. And then plus the first x times the derivative of the second. It's another log. So how do you take derivative of log? Fraction. What goes downstairs? The function. What goes upstairs is the derivative of cosine, which is negative sine. Okay, and now what should we do? We should not simplify. Why? Because it's set to. So we're done, and we move on. All right, number 2. We're going to find the equation for the tangent line to the implicit curve, arctangent y, quantity squared, plus xy equals pi squared over 16 at the point 0, 1. Good news. If we're looking for a line, we need 2 things. And they gave us 1 thing. Here's our point. So, what's missing? We need slope. How do we get slope? From derivative. So, slopes of tangent lines are derivative. So it's our great aha, we're going to do a derivative. Now, what kind of derivative are we going to do? Is there any clue? There's a huge clue. It's this word, implicit. Now, even if that word wasn't there, we'd still know this is an implicit relationship because we don't have a nice way to solve for y. So that's okay. Now, how do you do implicit differentiation? It's always the same idea. We look at it and say, oh, you know what? I'm going to think of y as being a function of x. Even though I don't know what the function is, I'm going to think of it that way. And now, starting there, I'm going to take a derivative. So, let's do that. So we have our arctangent of y, quantity squared, I'm going to write down for reference, equals pi squared over 16. And we are taking dx, taking the derivative with respect to x. Okay, so here we go. Chain rule. In fact, you see there's a function y, inside a function arctangent, inside a function square. A function and a function and a function. This is like a classic onion problem. Layers, lots of layers. So, derivative of the outside is the square. The 2 comes down. Arctangent of y to the power 1. Now, times the derivative of the inside. Derivative of arctangent. Well, take the derivative of the arctangent. By the way, love arctangent. It is 1 over 1 plus whatever function you're doing squared. But now I got to take the chain rule here. Okay, so what's the derivative of the y? Well, that's our dy dx. And okay, so now we finish the first term. How about xy? Well, product rule. So we're going to have the derivative of the first times the second, 1 times y, plus the first times the derivative of the second, dy dx. Now that's the derivative of the left. That equals the derivative of the right. And the derivative of pi squared over 16, 0. Great. Now, we have to do 2 things. Keep in mind, we are not asked to find the generic derivative. We're asked to find the derivative at that point, because that's our slope. So we have to solve for dy dx and plug in. Or plug in, solve for dy dx. Which one do we do? Well, if you're going to plug in, my advice is evaluate as soon as possible. But of course, not sooner. So let's plug in right now. Okay, so we're going to plug in. All right, so we're plugging in x equals 0, y equals 1. So everywhere where we see an x, we put a 0. Everywhere we see a y, put a 1, because that's our point, 0, 1. Okay, so we have 2 times arctangent of 1 times 1 over 1 plus 1 squared times the slope that we want plus 1 plus 0 times the slope that we want equals 0. All right, so that goes away. Arctangent of 1, okay, that's pi over 4. So we have a 2, and this is also a 2 in the denominator, which is a half. So if you think about it, we say, oh, those cancel. And now we have the following. We're to the stage where we say, look, pi over 4, this term, dy dx. And by the way, if you're looking at me and saying, how did you know that arctangent of 1 is pi over 4? Well, think about what arctangent is. It's the inverse tangent. So if I'm asking the arctangent of 1, it's the same question as saying tangent of what angle is equal to pi over 4. Tangent of what angle equals 1. And that's the pi over 4 angle. Okay, so pi over 4 times our slope plus 1 equals 0, so that we can move over is minus 1. That says our slope, dy dx, is minus 4 over pi. Okay, good, good, slope. Now, we're almost there. We've gotten our point, we've gotten our slope, so the last thing for us to do is to put it together and make a line. So, we get our y minus our y value is equal to our slope minus 4 over pi, x minus our x value. Or, we can rearrange this without too much work. We have minus 4 over pi x plus 1. So there we go. And there's our tangent line. And we're ready to go on to our next problem, where we use linear approximation to estimate f of 0.01, where f of x is 16 over log x plus 1 plus 2. Now, when we see the words linear approximation, we know it's really saying, hey, this is just code for tangent line. So there's a clue. Line shows up in linear approximation. So what's the idea? We're going to find the tangent line to this function, and then we're going to use that tangent line to evaluate. Now, tangent line where? You have to think about what's going on. Now, we're looking for f of 0.01. So here's how you figure out where the tangent line should be. 1, they might tell you. 2, you say, okay, they didn't tell me, but I know where I'm trying to approximate, 0.01. So I'm not finding the tangent line at 0.01. I'm trying to say, is there a convenient number nearby? So is there something near 0.01 which we can use? Well, I can think of one number near 0.01, namely 0.01 is near 0, and 0 is convenient, very convenient number. It's actually a lovely number. It's the kind of number we wouldn't mind taking home to meet the family. All right, so idea, right? We're going to take the derivative at 0 and get that slope. That gives us our tangent line at 0. And once we have our tangent line at 0, plug in 0.01. Whatever comes out, that's our approximation. Bob's our uncle. Life is good. Okay, so we need to do some evaluation. We need to find our tangent line. So, okay, let's plug in 0. F of 0. We'll need that information at 16 over log of 0 plus 1 makes 1 plus 2. Now, log of 1 is 0. Okay, so that's a very convenient number. So this becomes 16 over 2, which is 8. Now, how do we take a derivative? You might think quotient rule. That's fine. Quotient rule works. I'm always a little bit hesitant with quotient rule, and so I'm going to think of this in a slightly different way. So 16 times the quantity log x plus 1 plus 2 to the minus 1 power. Okay, it's true. This is the equivalent. And now, when we take a derivative, what do we get? Well, we have the 16, the minus 1 comes down, log of x plus 1 plus 2 to the minus 2 power, and we're doing chain rule. Don't forget the derivative of the inside. Well, times, what's the derivative of log of x plus 1? You put x plus 1 downstairs, the derivative of x plus 1 goes upstairs, and the derivative of 2 is 0, and we're done with the chain rule. Okay, but we're not done with the problem. We've got to evaluate this. You can rewrite this. So you say, look, there's a minus 16 on top, and then you have downstairs, there's an x plus 1 and a log of x plus 1 plus 2 squared. All right? So plug in 0. F prime of 0 is negative 16 over 0 plus 1, which is 1, times log of 1 plus 2 squared. Okay, well, 1 is 1. Don't need to worry about that. Log of 1 is 0. 0 plus 2 is 4. Sorry, 0 plus 2 is 2. 2 squared is 4. So this is negative 16 over 4, which is negative 4. All right, so we have found the information that we need, because to make a tangent line, we need to know two things, right? We need to know what's the value of the function, what's the value of the derivative, because that gives us information about slope, point slope. So our generic formula for linear approximation, sometimes it's called L of x, is this is f of a plus f prime of a times x minus a, aka it's the tangent line. So in our case, we say, all right, that's going to be f of 0 is 8, and then f prime of 0 is negative 4. So 8 plus negative 4 times x, and a is where we took our point, minus 0. Or if you like, that's 8 minus 4x. So, the final push. We have the information to get our tangent line. We put it in our tangent line, like a linear approximation. Finally, we say, our f at 0.01 is going to be approximately, what happens when we plug it into here? 8 minus 4 times 0.01. So that's 8 subtract 0.04, which is 7.96. Now, if you want more precision, of course, engineers always like 4 digits. You can add that on, but it doesn't really matter because the answer is 7.96. We're happy, life is good, and we move on to the next problem. When two resistors, R1 and R2, are connected in parallel in an electric circuit, the total resistance, R, is measured in ohms, and it's given by 1 over R is 1 over R1 plus 1 over R2. At a certain time, R is 1 over 6 ohms, R2 is 1 over 4 ohms, and R2 is increasing at 5 ohms per minute. If the total resistance is increasing at 2 ohms per minute, find the rate at which R1 is changing. Include units. Okay, now, side note. We have to make sure to include units. I'm going to make a note of that. I don't include units until the end. And here's the thing. Units work themselves out. They're highly, highly predictable. Okay, so let's think about what we have. We have a lot of information. We already have the formula that connects everything together. That's a big chunk of work. We know what kind of problem it is because what do we see? We see a relationship and lots of rates, right? We're saying, hey, here's something that's increasing at 2 ohms per minute. Here's something that's increasing at 5 ohms per minute, and find a rate. So it's like rate, rate, rate. So if you see a bunch of rates and the variables are related, it's related rates. Aha! Okay, so as I said, they did the hard work for us. Thank you, nice people. All right, well, so let's see what we have. Let's write down what we know. So what do we know? Well, we know the value for R, that's 1 over 6. We know the value for R2, that's 1 over 4. We know R2 is increasing at 5 ohms per minute. That says d R2 dt is 5. The total resistance is going up at 2 ohms per minute. So total resistance, that's your R. So dR dt is 2. And increasing means that it's positive. Now if it said it's decreasing, make sure you put that negative sign in. But we're positive. Okay, we're optimist here. I love that. All right, well, what do we want? And, well, the answer, we want to figure out the rate at which R1 is changing. dR1 dt. Okay, so with that in mind, we're about ready to begin. And, we look at this and say, well, take derivatives, right? So when you're looking at a related rates problem, sort of the key here, and this is sort of our thought process, is we're looking at this, and we say, well, really, R is a function of t. R1 is also a function of t, and R2 is also a function of t. So really what we have is we have 3 functions of t. So we're going to take the derivative of this with respect to t. All right, so here we go. So we're taking our relationship, and this is a time when I might clear out the denominators, but I think it would make things even worse. So we'll just embrace it and take a derivative. So derivative with respect to t. All right, so the derivative of 1 over r, think of it as r to the minus 1. The minus 1 comes down, and then it'd be r to the minus 2, so that's minus 1 over r squared, but we're not taking derivative with respect to r, with respect to t. So chain rule that. So dr dt. Now, the other derivatives, same process. Minus 1 over r1 squared dr1 dt, and minus 1 over r2 squared dr2 dt. Okay, now, good news. We know a bunch of stuff. Let's mark what we know. We know this, 1 over r squared, we can grab it. dr dt, we know it. 1 over r2 squared, great, we've got that. dr2 dt, great, we can find it. And what do we want? Well, we want this dr1 dt. Great. Now, you might notice something hasn't been circled. Uh-oh. We've got to get a handle on r1. So, we have to figure out what r1 is. But there's good news. Remember, these are related rates, which means there's relationships. So we're going to use our relationships. So, which relationship do we use? Well, we come up here. Say, hey, check it out. Check, check, check. Check it out. So, we plug in to our relationship. Say, okay, r is 1, 6. So 1 over r is 6 equals 1 over r1, which we don't know, and then 1 over r2 would be 4. So we're plugging this into our relationship to solve for r1. So you can subtract 4. So that says 2 is 1 over r1, or r1 is 1/2. So now we know. And we say, hey, this is great. We figured out this term, and the only thing left for us to do is to plug stuff in. Okay, before we do that, I'm just going to say, hey, since everything's negative, let's make everything positive. One less thing for us to keep track of. So this becomes r squared is 6. 1 6, but it's 1 over r squared, so this is going to become 36. dr dt is 2 equals 1 over r1 is 1 over half is 2, but we're squaring that, so that's a 4. dr1 dt, 1 over r2 squared, so 1 over 1/4 is a 4 squared, gives us a 16, and dr2 dt is 5. Okay, so we have 72 is equal to 4 times this rate that we want to solve for. 16 times 5 is 80. All right, move the 80 across. We get 72 subtract 80 is negative 8 equals 4 dr1 dt, or we could say, hey, that says dr1 dt is negative 8 divided by 4 is negative 2. Now, remember, include units. So, what is R1? R1 is being measured in ohms. So we put ohms per, what is T? T is minutes, right? Because it tells us minutes there, right? We see that rate. So, it's the same right here, minutes. So, it's ohms per minute, and we are done with that problem. We move along. Number 5. Let f of x equals negative x to the 5th minus 5x to the 4th plus 20x cubed plus 15. Okay, we need to find all open intervals where f of x is increasing or decreasing. Explain your answer. Now, increasing, decreasing, that's code. That's really saying, hey, you know what? Look at f prime of x. So that's what we're going to look at. We have f of x, so we start by saying f prime of x. Well, we see that is negative 5x to the 4th minus 20x cubed plus 60x squared. And the derivative of 15, 0. Good, good. Now, we factor that. And by the way, this is polynomial. We love polynomial. Polynomials are our friends, so we're really happy to see polynomial. Well, what do we have? Everything's a multiple of 5. Everything has powers of x. There's an x squared, so we're going to pull out negative 5x squared. Why negative? I like to have a positive coefficient in front of the leading term. So we'll be left with x squared in front of the first term. We pull out negative 20, negative 5 leaves us with 4x. And here we'd have minus, because we pulled out a negative, 12. Okay, good. Now, this x squared plus 4x minus 12 factor. If it's on a calculus exam, it's going to factor. Because why? Because they love us, and they didn't give us calculators. And so that's the trade-off, right? If there are not a lot of calculators, they got to give us things we can work with. So when we look at this, we say, okay, x squared plus 4x minus 12 factors as how? Well, we need to have two numbers that multiply to negative 12, add to 6. And we can think about it for a second. It doesn't take too long. X plus 6, x minus 2. That should do it. Always double check. X squared, good. Minus 2x plus 6x, good. Because that gives us 4x and minus 12. Life is good. So we say, where does this equal 0? Well, that gives us the following critical points. And namely, x equals 0, x equals negative 6, x equals 2. Okay, now, here's the thing. Why did we talk about f prime of x? So, increasing, that really is saying f prime of x is positive, and decreasing, f prime of x is negative. The reason we want to know the critical points is that's where behavior could change. Doesn't mean will change, means could change. So, we say, all right, let's draw the line, the number line. And we take the points. We have 0, negative 6, 2. Put them in order. So negative 6, 0, 2. And now we plug points in that are in between these values. So we say, well, let's start down here. Like negative 8. Negative 8. So this will be negative, and then you have a square, which is always positive. Negative 8 plus 6 is negative. Negative 8 minus 2 is negative. I'm not worried about the values. I'm worried about the sign. So we get negative, negative, negative. That's highly negative. And that tells us that the derivative is negative over here. Okay, what about, say, something between negative 6 and 0, negative 3? We'll get a negative from the first piece. Negative 3 plus 6 is positive. Negative 3 minus 2 is negative. Negative, positive, negative. Altogether, that becomes a positive. Between 0 and 2, we could pick 1. And we have a negative. 1 plus 6 is positive. 1 minus 2 is negative. Negative, positive, negative. And, it's still positive. And something bigger than 2. 3. 100. A million. But 3 is pretty easy. Negative. 3 plus 6 is positive. 3 minus 2 is positive. And so negative, positive, positive, we get negative. So what do we see? We're negative, we're positive, we're negative. Now, on a side note, why did we not change sign at 0? Because notice that it's an x squared. So it's a double root. I'm throwing out some technical terms. Double root. What? Yeah, so double root, we're not changing signs. Single root, we cross. So in algebra, single root, we cross. In general, if it's a root to an odd power, we cross. If it's a root to an even power, we bounce. And so in this case, because 0 has a double root, it bounces. And so we don't actually go across and change sign. Now, our explanation boils down to this part right here. And we say, okay, so we can say the following. F of x is decreasing where f prime of x is less than 0. Whenever they say explain your answer, you got to put in a, try to like do a sentence, because they're very persnickety. And this happens for which intervals? Well, for x below -6, because that's negative, and you can even say less than or equal to or less than, and x above 2. F of x is increasing where f prime of x is positive. Okay, so where does this happen? Now, if you look at it, you might say, oh, there's 2 places, right? There's from -6 to 0 and from 0 to 2. But they're right next door to each other. And you say, hey, you know what? You can merge them. So this happens for the interval -6 up to +2. And there you go. So if you have consecutive intervals where you're increasing and the function is continuous, don't forget that, then yeah, it's just always, you just one big interval. Okay, now that's part A. We have part B. Classify each critical point of f of x as a local maximum, a local minimum, or neither. Explain your answer. Now, we actually can get this really quick because we have all the work done. F prime negative means you go down. F prime positive means you go up. Positive, positive, you go up and up. And then you see a positive, negative, up and down. So, by the first derivative test, and we can use the first derivative test to do classification. We see that at -6, we are what? We're going down then up, down then up. So we are a local min. Okay? And by first derivative test at x equals 0, we are neither a max or min. And why is that? Well, because we're going up and up. We're not, it doesn't go up and down or down and up. It's up. So, nothing. And at x equals 2, well, what do we have? We're up then down. Up then down. What's that? Well, that is a local max. And there we go. So what's our explanation? First derivative test, and we'll even just point an arrow up there. All right, so, we've done it. Great. Well, that was actually surprisingly easy. Now, could we have done the second derivative test? Yeah, we could have. But once you've already invested to know things such as increasing, decreasing, you basically understand the function really well enough to do classification, which means we're happy enough to move on to number 6, our last one. Jack the gardener. Well, okay, nice to meet you, Jack. Wishes to enclose a rectangular-shaped garden within a given region, as is shown in the picture. They give us a picture. Find the maximum area of the rectangular garden if the boundaries of the given region are the x-axis, so there's the x-axis, the y-axis, and the curve, y equals minus x squared plus 12. Be sure to explain why your answer is the maximum area. Okay, now when you see something like this, where it says like be sure to explain or justify why, it's just saying, why are you at a max? Maybe you just gave Jack the smallest possible area. And okay, so we're going to deal with that once we get to that stage. So we look at it and say, okay, what's going on? Well, we have some natural dimensions here. It's a rectangle. And so rectangles, you can talk about the dimensions. We'll call this length x. We'll call this length y. And so what are we trying to find? We're trying to find maximal area. So we're going to maximize the area, which is x times y. However, we can't just take an arbitrary plot, right? We can't take a huge rectangle. There's a constraint. Now the constraint is in this corner, and you'll notice here that y is minus x squared plus 12. So we can put that in. So our area really looks like x times minus x squared plus 12. And so we can think of it as a function just of x. So now you give us an x value, and now you can't choose an arbitrary x value. The smallest x value you could pick is 0, but that would be a terrible garden because there's no area. You could also choose an x value all the way here, and that would be at whatever square root of 12 is. We'll call it 2 root 3. Again, terrible garden, no area. So there is this sort of implicit that 0 less than or equal to x less than or equal to 2 root 3 going on. But for now, we have our function we're trying to optimize. We've gone it down to one variable. That's the number of variables that we like. We are, after all, single variable, and so we take a derivative. Optimization says, hey, the max has to occur at a critical point. Now, I should have, before I took a derivative, actually done one more thing, which is, we'll do it now. Rewrite this as minus x cubed plus 12x. Okay, so the derivative is minus 3x squared plus 12. We're looking for critical points. It's polynomial, never undefined, set it equal to 0. This tells us that 3x squared has to equal 12. That tells us that x squared equals 4. Well, that tells us that x equals 2. Not plus or minus 2, 2, because it has to fit into here. Negative 2 would be over here. That's not part of our region. Okay, so we know x equals 2. Now at this point, we pause and say, what are we looking for? Are we looking for the dimensions? Or are we looking for the area? Or are we looking for something? And so we read it carefully again, and it says, find the maximum area of the rectangular garden, blah, blah. So we just need the area. We now know where it happens. So, and on a side note, if you just find 1, it's got to be the 1. It's got to be where it happens. That's not justification. We'll do justification in a second, but we know it's going to be at this value. So the max area is going to be a of 2, and that is going to be equal to a of 2, that's minus 2 cubed plus 12 times 2. It's minus 8 plus 24, which is 16. Now, did they give us any units? No, they didn't tell us what the distance is, so we don't know. Are these meters? It's probably meters, but 16. All right, so that's the max area. Well, we're not getting full points yet. We haven't done our justification. Why is this the max? Well, we've already kind of waved our hands. At 0, we have 0 area. At 2 root 3, we have 0 area, and we can't go outside between 0 and 2 root 3. I'm going to pull out a second derivative test because this derivative is super easy. So what would a double prime of x look like? Well, that would be minus 6x. And now, if you plug in a double prime of 2, that would be minus 12, which is negative. Well, why is that? Good to know. Well, if our second derivative is negative, our curve looks like that. If our second derivative is positive, our curve looks like that. And if our second derivative is 0, we have no idea what's going on. But the punchline here is the second derivative is negative, and so we say, aha, by the second derivative test, and this just takes a second to write down, since a double prime of 2 is negative, then the x equals to is a maximum. And there's a good justification. And that brings us to the end. Take your pen, drop it, because we're done. Life is good. All right, I hope you're doing well. Keep studying. You can do this. These are within your grasp. Work on it. You can do great.